Salutations, mini mathematicians. We are in section 6.2 already. So 6.2a, a proof of the Pythagorean theorem. So cool fact, Pythagoras wasn't a real person. It was a community of people. And they took their math seriously. So they believed that thoughts and ideas, they were possessions and that they owned them. So, in fact, there was a mathematician that came and visited them and kind of spread their ideas, their intellectual property around to the rest of the Western world. So they didn't like that. They put him into a ship and put the ship into sea and like shot fiery arrows at him. So, anyways, this theorem, amazing, didn't come from an actual person, came from a community of people. Look what you can do when you're a team, right? So today what we're doing is not setting anyone on fire, hopefully. We will be using scissors, so be careful. Be able to explore the Pythagorean theorem visually to find missing side lengths of right triangles. So this theorem says that for any right triangle with leg lengths A and B and hypotenuse C, hypotenuse is the leg length or the side length opposite the 90-degree angle. It's always the longest leg length, and you explored this last year in 7th grade with the triangle inequality theorem. And this, so Pythagorean theorem says a squared plus b squared will always equal c squared. Let's get started. So here, what I have is, in the problems below, a right triangle is drawn in gray, and the shorter sides of the right triangle are referred to as the legs, and the longest side of the right triangle is called the hypotenuse, which is always opposite the right angle. So something I always like to try and do is draw an arrow from the right angle to the hypotenuse to really identify it. It's important. So directions, squares have been drawn adjacent to the sides of the right triangle. Find the area of each of the squares. Assume each square on the grid has a side length of 1 unit. So like this would be a 1 by 1 square. Write the areas inside each of the squares. Okay, well, a square, if this side length is 2, the area is 4. And this square also has a side length of 2, so it has an area of 4. Okay, well, what about this other square? It's one of those tilted squares, you guys. So remember, we can make a perfect square on the inside and add these triangles, or we can make a perfect square on the outside and subtract these 4 congruent triangles. So if we took the, so it doesn't matter which one you do, if you want to add or subtract, why don't we take the perfect square on the outside, which is a 1, 2, 3, 4. So that's a 4 by 4 square. And we're going to subtract 4 triangles that are a 2 by 2. So 4 by 4, that's an area of 16. Minus 4 triangles. Area of a triangle is base times height divided by 2. So 2 times 2 is 4, divided by 2 is 2. So 16 minus 8 is 8. So this square has an area of 8. Okay. Do you notice anything interesting about those numbers? Maybe a relationship here? Okay. Let's move on to the next one. Go ahead, take a moment, find the areas of each of these squares, all 3 of them. So pause the video, find the areas of those squares, and then think, hey, do you see a pattern? Okay, so that should be enough time. So maybe you found that this has an area of 4 square units, this has a square area of 9 square units, and this has an area of 13 square units. Do you notice anything yet? Well, what do we notice about the relationship between the areas of the squares formed adjacent to the legs? So what about the ones connected to the legs and the square formed by the hypotenuse? 4, 9, 13, 4, 4, 8. Yes, I know we both have a 4 here, but there's something bigger. What do you notice? Well, the sum of the leg squares, remember the legs are the shorter sides, is equal to the hypotenuse square. Interesting, interesting. So what we have here is that we know that if we have a right triangle with leg lengths A, B, and hypotenuse length C, we can draw squares using the leg lengths. So this would have an area of A squared, and this would have an area of B squared. And this would have an area of C squared. And we know that because the side length of a square squared is the area, and the area of a square square rooted is the side length. So, and we notice that A squared plus B squared is equal to C squared, the Pythagorean theorem. So we're going to look at this visually a couple different ways. Something else I want you to take a look at is on our calendar and on your Google Classroom. There's a couple of proofs. There's 4 video proofs that would be fun to watch at this time. Okay. And so we saw that in the previous problem, we found that for two specific right triangles, the sum of the areas of squares along the legs of the right triangles equals the area of the square along the hypotenuse of the right triangle. So does this relationship hold true for any right triangle in the whole wide universe? The galaxy? Well, suppose you have a right triangle with any side lengths A, B, and C, where A and B are the legs and C is the hypotenuse, as shown here, and the squares have been drawn along, just like we drew on the previous page, but maybe a little bit more to scale here. So the first thing says, find the area of each of the squares adjacent to the sides of the right triangle and write them inside each square. So this is going to be a little activity on following directions. So reading these directions for 4, 5, and then 6, I want you to follow them. So that this means like we're writing the area of all of these squares. So since this square has a side length of A, the area is A squared. Little a, B squared, and C squared. Okay, now it wants you to cut out just the squares formed by the sides of the right triangle above. So you're going to cut out this square, and this square, and the 8 copies of the triangles below. 1, 2, 3, 4, 5, 6, 7, 8. So you're going to have 8 triangles and 3 squares cut out. And we're going to go to the next page. So after you cut those out, so you can pause the video and cut them out now if you want. Be careful. Were you careful? So now we have these 2 squares that are congruent. And since the squares are congruent, like cookie cutters, same, they have the same side length and the same area. So we want to arrange the 3 squares in 8 triangles to cover the 2 squares below. So maybe some of the squares will be in square 1, some will be in square 2, and some of the triangles will be in each of them. So remember, you have your C squared, you have your B squared, and you have your A squared. And then you have 8 little triangles that have A, B, and C also labeled. If you cut out the middle of the square that has a right triangle, notice that one doesn't have A, B, and C labeled. So don't use that one. So maybe we can fit these in here. So that they might overlap a little bit if you didn't cut out the sides. Let's see. How can we get these to fit? How can we get these all to fit in here? So go ahead and kind of play around with these to see if we can get them all to fit. How can we get the 8 triangles and 3 squares to cover these 2 squares? So I'd like you to take a moment, figure those out, and then I'd like you to work on 7, 8, and 9. So go ahead, read 7, 8, and 9, and we're going to go over those in just a second. Okay, hopefully you had some time. So what I found worked best is if we have to use all of them, we are going to use c squared in the center as a tilted square, and we're going to be able to fit the triangles around it. And square 2, you're going to fit the b squared and the a squared, and then the other 4 triangles here. So maybe you switch swap square 1 and square 2. That's totally fine. So 7 says, what's the area of square 1 in terms of A, B, and C, and show all your work. So my square 1, notice your square 1 and square 2 might be switched. So square 1 for me, I have the area of 4 congruent triangles, which all have a base of A and a height of B. And I have a square that's C squared. So if I'm making up the area of this square, I notice it's 4 AB divided by 2 because each triangle has a base of A and a height of B. An area of a triangle is base times height divided by 2, plus C squared, which is the area of the square. Many of these Pythagorean theorem proofs, you guys, they're going to take the areas of the items that are making up the shape and adding up each area to find the sum of the area. So that's what we're doing here. And then, of course, this 4 and this 2 cancel, and the 4 becomes a 2. So I have 2ab plus c squared. So that's the area of my first square. And then the area of my second square, well, if I take the parts apart, I have my 4 triangles again. I have my 1a squared, and I have my 1b squared. So notice I have my b squared, I have my a squared, and I have my 4 triangles. Maybe yours are taped or glued down. That's perfect. So from here, we know that the 4 triangles have an area of 2ab as discussed before. There's 4 of them, base times height divided by 2. And then a squared plus b squared. So 2ab plus a squared plus b squared. But like we said from the very beginning, these 2 areas are equal to each other because the 2 squares are congruent up here. So since they're congruent, they have the same area. So if we set them equal to each other, and notice that we can subtract 2ab from both sides, we end up with the Pythagorean theorem. So cool. So since both squares are congruent and have the same area, we can set the areas equal to one another. And using the property of equality, subtracting the same amount from both sides is still equal. We see that c squared equals a squared plus b squared. So for any right triangle, the sum of the areas of the leg squares is equal to the area of the hypotenuse square. So radical. Okay, so we are going to apply this to 10, 11, 12, and 13. So the direction says determine the area of the third square and write your answer in the square. Determine the value of the legs and hypotenuse for each triangle and write the values below each picture. Verify your side lengths using the Pythagorean theorem. Again, something I find super helpful, you might want to write yourself a note, is drawing an arrow from the right angle to the hypotenuse C, and that's just going to help us remember or see which is our c squared for a squared plus b squared equals c squared. So that's going to be helpful for us. We can do that to all these problems because visually sometimes you can't really tell which one's the biggest. So here we have a squared plus b squared equals c squared. So this is going to be 1 plus 36. So the area here is 37. So the length of our legs, remember, the length of the legs is the square root of the area. It's the side length of the square. So I have the square root of 1 and the square root of 36, which of course we want to simplify. So we know it's 1 and 6. And you can say units here if you want to. So the hypotenuse in simplest radical form is the square root of 37. Notice there's no perfect square factors of 37, so that's in simplest form. And we're going to verify with the Pythagorean theorem. So always write the theorem to begin with. A squared plus b squared equals c squared. From here, substitute in the numbers. So 1 squared plus 6 squared is equal to the square root of 37 being squared. Following order of operations, 1 squared is 1, 6 squared is 36. Square roots and squares are inverse operations, so 37. And yes, 37 is equal to 37. So we're not done until we get a true statement. Groovy. Let's take a look at 11. So 11, very similar, but a little different. Notice they give me a leg square and a hypotenuse. So since a squared plus b squared is equal to c squared, since a squared plus b squared is equal to c squared, if I'm just looking for b squared, I know b squared is equal to c squared minus a squared. So if this is 29, this is 4. 4 plus what number makes 29? Or you can think about this as 29 minus 4, which is 25. Okay, so what are my legs? Remember, we drew that arrow to the hypotenuse. So the legs are the square root of 25 and the square root of 4. So that means it's 5 and 2 units. So the hypotenuse in simplest radical form is the square root of 29. Double check. Is that in simplest radical form? Why, yes, it is. So we can keep going. Verify with Pythagorean theorem. A squared plus b squared equals c squared. You have to write the theorem first. Okay, we're plugging in the values of the legs. So 5 squared plus 2 squared. And notice a and b are interchangeable. They're being added. So it doesn't matter if I say 2 squared plus 5 squared or 5 squared plus 2 squared. Commutative property of addition equals c squared, which is the square root of 29 being squared. 25 plus 4, square roots and squares are inverse operations. And 29 is equal to 29. Yay, true statement. Okay, so what I'd like you to do is pause the video, finish 12 and 13, and we'll go over it as soon as you are ready. Okay, let's take a look at 12. Taking a look at 12, our missing area of the square is 4. So our leg lengths are square root of 4 and square root of 4, which is 2 and 2. The hypotenuse in simplest radical form is square root of 8, which we know is 2 square root 2. Don't forget to simplify. And then verify using the Pythagorean theorem, a squared plus b squared is c squared. So we know that this is true. Notice if you're thinking about 2 square root 2 being squared, we can think about this as 2 square root 2 times 2 square root 2, which is numbers on the outside times numbers on the outside, 2 times 2. And then numbers on the inside times numbers on the inside, 2 times 2. 4 square root 4, 4 times 2, which is 8. You can also think about this as 2 square root 2 being squared. You can put this number back on the inside by squaring it. So this would be 4 times 2. So this is just the square root of 8 being squared, and squared and square roots are inverse operations. So that's how we can also get 8. You can also think about squaring this 2 to get 4, the square root of 2 to get 2, and 4 times 2 gets you 8. So a couple ways you can think about squaring square roots when you have a number on the outside and a number on the inside. Nice. Okay, and make sure you are working all the way to show a number equaling the same number. And on 13 here, we had 2 leg squares given to us. So 16 plus 36 is 52. So our legs are 4 and 6, square root of 16 and square root of 36. Our hypotenuse in simplest radical form is 2 square root 13. So from here, remember 52 is 4 times 13, square root of 4 is 2. Using Pythagorean theorem, a squared plus b squared equals c squared, I just used my original unsimplified value to do the math here. I found it a little bit simpler for me than thinking about 2 square root 13 squared. And then I ended up with a true statement. Yay, us! Okay, so we're going to work with our new skills of Pythagorean theorem to draw some shapes. So I know we've been working with drawing some tilted squares and it's been a little tricky, but now it's going to be way more efficient with our new theorem. So on the grid, we're going to use our knowledge of right triangles and the Pythagorean theorem to conduct a square ABCD with an area of 40. Okay, so before we used to have to be like, oh, maybe this perfect square will work, maybe I can subtract 4, and it was pretty confusing. And if you think it was easy, good for you. Proud of you. So taking a look, the first thing we're going to do is think of 2 perfect squares that add to be 40. And sometimes what I like to do is make a quick little sketch of what I'm going to be drawing. So like A, B, C. So I want this to be 40. So I want 2 perfect squares that add to be 40. Thinking of them, thinking of them. Did you think of 2 numbers yet that are perfect squares that add to be 40? And if you needed to rewrite the perfect squares up here, you can. 1, 4, 9, 16, 25, 36. That's all I'm going to need to think about 40 because obviously I have to add numbers that are less than 40 to make 40 because we can't have negative numbers here. Can't draw like a negative area. So here to make 40, it's 36 and 4. Okay, so then our next step is use these to draw a right triangle with the square roots as the legs. So what do I mean? Well, the square root of 4 is 2, and the square root of 36 is 6. So I'm going to need a 2 by 6, 2, 4, 6. So 2 by 6 to create my right triangle. Now what we're going to do is we're going to use slope to draw the hypotenuse square. So what I mean is, since I'm going down 6 and right 2, and I know that a square has opposite sides that are parallel, so they have the same slope, and adjacent sides that are perpendicular, meaning their slopes are opposite reciprocals, I can go down 6, right 2, which means I can go right 6, 1, 2, 3, 4, 5, 6, and up 2 to get to the next vertice. And of course, opposite sides are parallel. So I'm going to go up 6, 1, 2, 3, 4, 5, 6, and left 2. And notice that this makes it look like a square. If when you drew it, it didn't look like it had right angles, if it looked like it was more of a rhombus or like a weird parallelogram, you know to redo it. And notice they called this A, B, C, D. So we're just going to go in alphabetical order, A, B, C, D. And you can start that A vertice anywhere as long as you're going in alphabetical order around your shape. So A, B, C, D. So this is square A, B, C, D with an area of 40 units squared. Ta-da! So beautiful. Nice. Okay, so let's take a look at what else we can do. So on the grid below, we're going to use our knowledge of right triangles and Pythagorean theorem to construct the following objects. So make sure you're labeling your vertices. Vertices are always labeled with capital letters. And we're going to write the slope for each segment, and we're going to clear label the vertices. So we're going to do square PQRS that has an area of 10 square units, segment EF that has a length of square root of 41 units, and segment LM that has a length of square root of 68 units. So first things first, I'm going to help you out with B, and then you can do A and C on your own, since A is pretty similar to what we just did above, and C will be similar to what we do in B. So taking a look at B, if we want just a segment that has a length of 41 units, so if we think about our right triangle we're going to make here, I always like making a plan. We're going to have the square root of 41. So this area will be 41. So we need two perfect squares that add up to be 41. So if we go back and think about our perfect squares, and we would find that 25 and 16 add up to be 41. So we're going to have 5 and 4. So again, all we need is a right triangle with side lengths 5, leg lengths 5 and 4. And then this part will be EF, which will be square root of 41. So showing our work up above, so that part B, all we need to do is go down 5. So 1, 2, 3, 4, 5, and over 4, 1, 2, 3, 4. And I'll label my lengths 5 and 4. And then sometimes I like just using a different color to show I'm not really drawing the triangle. What I care about is this segment, and this segment is EF. You can label it FE if you want. So this is EF, and it is the square root of 41 units. Really nice job. Okay, so take a moment, go back and make your plan for A, make your plan for C, and then create them. Don't forget your labels, pause the video, and we'll go over the answers as soon as you're ready. Okay, so let's take a look at how we did. So when I was working on A, I know that A squared plus B squared is C squared. So I had to think of two perfect squares. So going back up here, think of two perfect squares that add up to be the area that you want. So that's 9 plus 1, which gets me 10. So I know the square root of 9 plus the square root of 1, square root of 10. I guess these would be squared. So we know that our leg lengths are 3 and 1 to get that 10. So for here, I had 3, 1, and then I used the slopes over 3 up 1, up 3 over 1, over 3 down 1, and labeled my vertices P, Q, R, S with 10 labeled in the middle. Oops, this was square root of 41. So segment EF we did together for part B. For part C, I just needed segment LM that has a square root of 68 units. So here, I knew what two perfect squares added to be 68, 64, and 4. So thinking about our little area model here, I know that 64 and 4 make 68. So my leg lengths I needed were 2 and 8. And then LM would be the square root of 68. And I didn't have to draw any extra squares because I just wanted that segment. So you're pre-planning, you might draw the squares around the triangle, but then when you actually go to draw it, just to save space, just draw what you need to create the object you're creating. May it be a line segment or a square. Awesome. Great job, mini mathematicians. Excellent work with Pythagorean theorem. Hope you had some fun, and don't forget to watch those other proof videos on the calendar. Enjoy, stay psyched, do your best, be nice to everyone, and I'll see you next time.